Hello, my name is Kevin Day. This presentation is titled Internet of Things Computing. This presentation was part of my Virtualization and Cloud Security graduate course at Metropolitan State University in St. Paul, Minnesota. The Internet of Things is playing a key role in transforming everyday life, adding increased device connectivity and functionality while generating data faster than most applications can process and filter. By combining connected devices with automated systems, it is feasible to gather information, analyze it, and create actions or events to help gather additional information from a process or a task. IoT is a system of interconnected computing devices which include mechanical and digital machines. Each IoT device is equipped with a unique identifier UID and can collect, share, and analyze over a network without requiring human-to-human or human-to-computer interactions. IoT is a collection of heterogeneous entities in which entities refers to human, sense, or anything that may request or provide a service. As more types of wireless networks become available, the total number of IoT devices around the world will expand the market of IoT devices and applications. Vendors are implementing Internet Protocol version 6 addressing schemes in combination with high-speed internet connections to improve the design and performance of IoT networks and devices, resulting in increased growth and demand for new IoT products. Unfortunately, many IoT devices have operational and physical limitations on the computational power available to them. These constraints often create challenges concerning implementing basic security measures due to the focus of developers on low price points and consumer convenience of IoT devices and applications, which makes robust security patching of security and applications uncommon. The lack of unpatching and updates within the IoT community has created significant challenges with maintaining secure networks that contain IoT devices. The first reference model for IoT established a standard model for IoT systems and application. The initial proposed reference model consisted of 3 levels and represented IoTs as wireless sensor networks. In 2014, Cisco published a white paper on new IoT reference model. This model expanded the initial layer to 7 layers. Level 1 devices. Physical devices are located at the edge side and include devices such as smart controllers, sensors, and radio frequency identification RFID readers. Data confidentiality and integrity originates at this level and continues upward. Layer 2 connectivity. All protocols and processing units that allow for the transmission of data or commands by using routing and switching protocols are contained in this level. Level 3 edge computing. Basic data procedures start off at this level and is necessary for reducing the various computational loads that occur at higher levels. Expedient responses to events and different learning algorithms are implemented at this level. Level 4 accumulation. Data is combined from multiple sources and converted from transit to rest. The data in transit is converted into a queryable format, then filtered and selectively stored, by which data of interest is forwarded on to higher levels. Level 5 abstraction. Data is read and stored in a manner that is both simple and effective. Services at this level may include data normalization or denormalization, indexing, consolidating data into one place with access to multiple data stores. Level 6 applications. The accumulated data can be interpreted with different levels of software abstraction. And level 7 collaboration. Users and business processes using IoT applications and their analytic data can make informed choices or corrective actions. IoT applications have created a massive amount of data organizations can collect, analyze, and store. What makes up the concept of big data is large and complex data sources from various sources to predict outcomes and make recommendations. This data is so voluminous that traditional data methods cannot process it effectively. Thus, artificial intelligence and machine learning are being implemented to help with big data analysis. The 4 V's of big data. Volume. Data is collected from a variety of sources. This is an incredible amount of collected data that is difficult to process and store using traditional analysis methods. Variety. Digital data cannot be transformed in traditional simple data formats delivered by applications in all types of formats such as database files, CSVs, or non-traditional database formats such as PDFs. The velocity or speed, the rate at which data is generated from an IoT application, happens at an unprecedented speed. This accumulated data must be handled in an appropriate manner to remain pertinent. Veracity, or the quality. The quality of data depends on certain factors such as where the data originated from, the method collected, and how the data will be analyzed. A high degree indicates the data has many records that can be analyzed in a meaningful way, whereas a low velocity contains a high percentage of data that is unintelligible or meaningless. The explosion of IoT devices and applications has expanded the device and application market into new business opportunities and revenue streams. Many devices implement IoT services to have a better understanding of operational expenses to increase more focused marketing campaigns using insights based on consumer behavior and product placement. Implementation IoT for targeting marketing campaigns can lead to the reduction in a production lead time required for products to become available to customers. Additionally, IoT offers just-in-time training for employees, improving labor efficiency and increased organizational productivity. Logistic and supply chains are more robust using IoT technology to create a unique identifiers for items inside multiple supply chains, allowing for intelligent choices to be made on how to deliver goods and services in a timely and efficient manner to distributors and customers. IoT devices have moved onto the utilities market with specialized IoT devices that allow for more efficient monitoring and administration of utility services. Water, gas, and electric meters have moved onto being able to be read via apps and wireless built into the meter. In past, meters were read manually by a utility employee who walked up to the meter, recorded it, and the numbers were displayed on the meter itself. The oil and gas industry are taking advantage of real-time IoT monitoring systems to ensure the safe transportation of fuels from production areas and storage facilities. The objective of a real-time leak detective system ensures that once a leak is detected, that an immediate alert is sent to an operator in a control room to take a corrective action depending on the nature of the fluid and estimated leak size. This allows for a more constant observation of pipeline from a centralized location. And just to put things in perspective, the U.S. alone has around 3 million miles of transportation pipeline of natural gas. Utility companies are also leveraging IoT devices to monitor the status of sewer lift stations and water treatment plants. When a leak or other event is detected, proper personnel is notified for the event to be investigated and determine if repair or corrective action is needed. Many medical facilities are starting to use IoT applications to improve patient care. With this explosion into the medical field, the need for secure IoT devices, application, and cloud services have become a hotly debated topic. Applications of IoT technology in the medical field include the following: heart monitors, harnesses that can be worn outside the hospital to monitor heart issues, insulin pumps and glucose monitoring systems that can regulate insulin administration, which can be controlled via smartphone app. and also wireless electrocardiographical EKG devices that can fit in your pocket and can be used as needed with results viewable on a smartphone app. Cloud computing. Cloud computing is a collection of many servers which have the characteristics of centralized data storage location access to shared computer resources. The process of delivering computing services can take place over a network using an internal network private cloud or a global internet public cloud, which can be a large and highly scalable deployment. Ultimately, resources and services provided by the cloud often is preferred platform for IoT deployments due to the storage analytics being performed in a centralized platform. Data and applications are available to users over the internet, covering a large geographical area and allow for performing computationally intensive tasks without a local data center in each location. Cloud providers are also incorporating an assortment of pre-packaged services for IoT operations by offering access to cloud services based on data usage, the amount of memory used as an alternative to owning and managing private data centers, choices made at which services and data should be migrated to the cloud and which should be filtered out. Also, the transferred data must comply to any applicable laws and regulations. Other considerations may include how access will be granted to data once it has been uploaded. Many cloud service providers will support web architecture based on application program interfaces, while others support traditional block and file-based data. Creating a cloud data center for processing IoT generated data can present computational challenges for time-critical applications, which can suffer from poor performance when network bandwidth is insufficient or exhausted. Data latency bandwidth exhaustion creates unique challenges for IoT applications in which milliseconds can result in less than ideal outcomes and fatal errors. Many applications continuously monitor and produce sensory input that is generated at a high rate. If a logic condition is triggered within the device, instant analysis and response is required for corrective or life-saving action. There are four major network factors that affect all internet communications, and IoT and cloud services are not immune to throughput, bandwidth limitations, latency, and jitter issues. Throughput is defined as the measurement of successful messages delivered over a selective communication channel. Bandwidth, which is the maximum rate data can transfer over a selective route. Latency, which is the measurement of time from which a message is sent and when the source destination receives the remote destination reply. Jitter is the variance in the total latency values over a set period of time. IoT and cloud services that provide audio, video, or voice services are negatively affected by latency and jitter. Services that are least impacted are email data transmission, which are delivered using Transmission Control Protocol or TCP. Video streaming, conference call, and video chat, and voice over IP or VoIP phone services are sent using User Datagram Protocol or UDP, which does not provide error checking. Video streaming is less affected because the video and audio may skip but continue to stream despite every packet being received. IoT devices must be closer to the data itself because they lack processing power and storage resources to perform analytics and machine learning tasks. Unfortunately, IoT devices cannot process data quickly enough for modern business applications, and even though cloud servers process computational power to process data quickly, they are located too far away to respond in a timely manner. IoT devices cannot process data quickly enough for modern business applications. By the time data has reached the cloud due to latency or bandwidth issues, the opportunity to use the data appropriately might expire. Furthermore, sensitive data should always be processed closer to the network edge where the data is generated. And now this is the section of fog and edge computing. Businesses and organizations are facing an increased need to analyze and respond to real-time data at the network edge. Edge computing is a distributed computing architecture that places applications as close to the origin of the data as possible. Edge computing devices are located at the logical edge of the network to minimize the distance between users, applications, or IoT devices. Edge computing moves portions of the storage and computing out of a central data center and minimizes the need for data to be sent to a remote cloud or another centralized system for processing. Edge processed data is sent to the data center for review, archiving, and merging with other data streams for broader analysis. Data is normalized and analyzed at the data center to provide data for business analytics, only returning the result of the analysis to the user. By using edge computing, data latency is improved between user and the cloud service, which increases the speed and performance of data transport. An edge device can be defined as a computing device which was built for a single function that possesses processing and network capabilities, providing an entry point and controls the flow of data at the network boundary. Using IoT edge devices can incorporate a more comprehensive range of device types and functions, which include sensors, actuators, and IoT gateways. There is a wide range of edge devices that can be implemented within a network. These devices can come in many different forms with a distinct purpose and make different assumptions about the data it generates, and as often comes installed with vendor-specific operating systems. The benefits of implementing edge devices include expanded access by enabling client devices to access networks and resources that would otherwise be inaccessible, increased device management, and reduction in administrative costs, which can allow for additional devices to be installed across the network. Other benefits of implementing edge computing include increased communication capabilities, more processing power at data generation, device data intelligence, and programmable automated controls. The drawbacks to implementation of edge computing within a network is the creation of a new threat vector to mount a defense against. Additions of newer features and device capabilities open the door to new opportunities for malicious actors to compromise devices. Vendors are deploying some built-in security capabilities, but many network engineers must develop a strategy to deploy these features and patch each device to prevent exploitation. Increased features can cause network bottlenecking if the network environment fails to provide enough throughput to handle the generated traffic of data. Fog computing. Fog computing architectures provide greater data analysis and management features to IoT applications. Emergent technologies that use distributed computing may allow for applications to be located as close as possible to the point of data creation, deploying one centralized computing device as possible for processing data from different endpoints, allowing for a significant amount of processing, storage, and communication to be carried out before transferring sensitive data to the cloud for historical analysis, big data analytics, or long-term storage. The fog computing standard defines how edge computing should facilitate the different operations of computational storage and networking services between IoT devices and cloud data centers. This brings data closer to users as compared to storing data far from endpoints in data centers, providing location awareness, low latency, and improves the overall quality of service. However, implementing a fog architecture can provide a large network of sensors and devices that can generate data across an extensive geographic area that is too large to define a logical network edge. Processed data is most likely to be needed by some device that has generated the data. So by processing locally, the latency between input and the response is minimized. An IoT device From an IoT device, data is read from a sensor in real time, then forwarded to a fog machine for analysis. And once the data has reached the fog node, the data can be filtered and sent on to the cloud for further processing and storage. The cloud data center receives the data from the fog device for a complex analysis, storage, or archiving. The advantages of implementing fog computing is reduced bandwidth, since fog computing has a significant effect on reduction of bandwidth and communication traffic between edge devices and the cloud. This greatly reduces the total volume of data that is required to be sent to the cloud for further processing and storage. Increased response time, moving the data computationally closer to where the data originated, the data latency is greatly reduced, and responsiveness is increased. The goal is to provide millisecond level in which data can be processed in real time. And network independent. Fog computing places computational resources at the local area network level, which allows the network to be a considerable part of the fog computing architecture. The releasing network can be wired, Wi-Fi, or 5G. The disadvantages to fog computing could be physical location. Since fog computing is tied to a physical location or area, it falls short of the anytime, anywhere benefits associated with cloud computing. Startup costs. Fog computing is a solution that utilizes both edge and computing resources, which is associated with increased hardware cost. Ambiguous concept. The concept of fog computing has been around for several years. However, there is a debate among developers and vendors on what the exact definition of fog computing is. Fog computing includes a diverse number of devices that store, analyze, and send their own data and are located in different regions of the world. Data storage. Data is stored on the device, which is located outside of the company's network or network boundary. This means that some businesses and organizations may be unwilling or cannot simply accept the security risk that sensitive data is not kept on premises. Now comparing fog and edge computing together. Both fog and edge computing can provide the same capabilities in terms of forwarding both data and intelligence to a cloud analytic platform from the point of data origin. Edge computing is when data is processed on the logical network edge on a local device or server rather than being transmitted to a data center. This pushes communication capabilities, processing power, and intelligence data directly into devices. Programmable automation controllers thus analyze data locally and closest to where it was generated in real time without transferring the data distant cloud data centers. Fog computing. Fog computing is the logical layer between the cloud and the edge device. This takes the raw intelligence data from IoT devices to the local area network and processes the data in either IoT gateway or fog node, acting as a mediator between the edge device and the cloud. However, this may create more physically distant from the sensor input and controlling mechanisms. And now we're going to discuss some brief vulnerabilities of IoT systems or networks. Security is a significant challenge for companies to adopt and deploy IoT innovations. There is not much motivation for vendors to change with little or no consequence for selling insecure devices, since the device can be manufactured very cheaply and are not maintained with regular patching and updates by vendors. IoT systems are at a higher security risk for other reasons: insecure network interfaces or services, insufficient authentication or authorization. These systems might include data or services that were not designed to be connected to the global internet. These systems may not have a well-defined parameter and are highly diverse in characteristics with respect to communication mediums and their protocols, platforms, and devices. As a result, IoT systems or portions could be physically unprotected and/or controlled by different parties. Also, IoT devices could be autonomous entities that are controlled by other devices. Routing attacks against IoT networks will affect how packets are routed by being spoofed, redirected, or misdirected to other networks. An attacker can inject fraudulent packets into communication links using three different methods: insertion, manipulation, and replication. There are several communication vulnerabilities in IoT devices, sometimes because of a lack of transportation, encryption, and integrity verification. This may cause packets to be unintentionally listened to private conversations over communication lines by a third party. As a result, there are several privacy concerns with IoT devices, such as insufficient security configurations, insecure software, firewall, and poor physical security. An, an example of a major security concern for integrated circuits is hardware Trojan. A malicious modification of an integrated circuit IC enables an attacker to use the circuit or exploit its functionality to obtain access to data or software running on the integrated circuitry. These attacks then can cause the IoT device to open and be vulnerable for further attack or use for botnets. Another type of attack that can occur is a Trojan attack. This can be through one of the vulnerabilities discussed earlier, or it can be through a supply chain attack where the hostile code is built into the device and can be active on a set time or predefined trigger activity. These could be externally activated by an antenna or a sensor, or internally activated by a given logical condition. A distributed denial of service or DDoS attack is a malicious attempt to make a service or network resource unavailable to users. The direct result of a DDoS attack are the temporary unavailability of resources and services to legitimate users. The goal of the attack is to overwhelm the target application with an overwhelming number of requests per second that require high CPU and memory usage and exhausting available resources. Multiple machines are used to target vulnerabilities and flood the target with packets, requests, and queries. Application-type DDoS attacks occur by deploying HTTP floods or zero-day assaults. These attacks are a standard way of attacking IoT devices that jam the transmission of radio signals by either continuously jamming, by blocking all transmission, or intermittent jamming by reducing the performance of systems. There are three well-known types of DDoS attacks against edge computing nodes: battery draining, sleep deprivation, outage attacks. When a battery draining attack usually happens because nodes usually must carry a small battery with a very limited energy capacity. In the sleep deprivation attack, the victim has a battery-powered node with a limited energy capacity, and the attacker attempts to send an undesirable set of requests that seem to be legitimate. And lastly, an outage attack happens when an edge device outage occurs when an edge device stops performing its normal operations. and then some brief countermeasures. There are new and emergent challenges to securing IoT systems, such as the dramatic increase in the number of weak links and unexpected uses of data. The dramatic increase in the number is because of the specialized characteristics of devices and cost factors by device manufacturers, such as compact battery devices with limited storage and computational resources. Many market devices are not able to support secure cryptographic protocols. A network administrator should always monitor traffic on network devices. Often third parties will attempt to gain unauthorized access to control over IT devices using the network terminal, often to spread malware. Some well-known ports to disable would be port 23 Telnet, port 2323, which is a TCP and UDP port, and 4800 101 used by botnets. Another important thing of a user of IoT devices can do to secure their devices to update the firmware of the device as soon as possible. Update the device with security patches from the manufacturer when available. Even if a device has a known software vulnerability, patch, or workaround might not be downloaded for an acceptable prolonged period. Thus, intrusion detection techniques have become more important. Many devices will notify you when an updated version of their OS is released, but for some it is necessary to go on with their respective apps or software suite to check for updates. Setting up an automatic software update will save the hassle of needing to check the respective app or software for updates. In conclusion, fog and edge computing will continue to increase as IoT expands and is deployed in new sectors of business. With continued growth in research and development, expect computation to be moved even closer to the network edge and become ingrained in the devices that are generating the data. Cloud computing will continue to have a significant role in the IoT data lifecycle, taking on heavier and more computationally intensive analysis. There is an increased demand for IoT devices and application. This has resulted in being a more frequent target of secure breaches and attacks. With the continued expansion of IoT demand, security impacts must be taken into consideration when developing and deploying IoT devices and any market or network topology. As with all technological advancements, improvements must be made in how IoT devices operate and how they are deployed on different network environments to minimize the potential security risk and attack surfaces. These are the main references I used within my presentation, and I hope you enjoyed this presentation, and thank you again for listening.